Hello, my people. Here we are with our video lesson for lesson 3.1, Exploring Relatedness. As you can see, this lesson has 4 parts. However, if you're listening to this video, that means you're a remote student. So we're going to have to skip the hands-on, unfortunately. I couldn't figure out a way to make this go virtual. So we're only going to do 3 parts. By the way, if you are an A group or B group student, read the instructions. You are not supposed to be doing this on your own. You should be doing this activity in class when you're in the building with you. Hey, now that housekeeping's been taken care of, let's dive into our warm-up. And I apologize, I do want to reset my lesson. I'm not giving away answers. So, here we go. We've got one of our evolutionary trees with an ancestor population and descendant species. And this is kind of the basic, right? We're going to go a little step deeper. So up here, there was a change or a split in the population where there were 2 different environments. Here, you'll notice it happens again. And so we have multiple species over on the right now. What I want you to do is kind of analyze this and answer these 2 questions down below. Which group of descendant species is most likely to have body structures that are most different from the ancestor population? And which descendant species is most likely to have body structures that are the most different from descendant species B? Okay, so I'll let you answer those. Go ahead and pause the video and answer those, and then I'll meet you on the other side. So friends, hopefully for this first one, we would have recognized that if we're talking about the ancestor population, descendant species 1 and 2 are just kind of one rung down in our tree, where there's another change in both of these species, and they're split again into different descendant species. And we want to know which one's most different, right? So we should be thinking that the descendant species A, B, C, and D are going to most likely be the most different from our ancestor population here. And then this one, we are going to compare species B with species 1, C, and A. So which one is probably going to be most different from B? Is it going to be descendant A? Is it going to be descendant species 1? Or is it going to be C down here in this other rung, this other branch of the tree? Hopefully our brains have kind of pointed out that, well, species A, B, and species 1 are all kind of together on the tree, while species C is separated, and it's had more changes in its environment. So we should be thinking C is correct. Let's go over this vocab term real quick. Related. I'm not talking about your brothers, sisters, cousins, any of that. Related in evolutionary terms means that there's a sharing of a common ancestor population. And according to the theory of evolution, we're all related then, right? So like I said, part 2, we're going to have to skip that one. And we're going to go straight to our modeling tool. We want to click that open right away because it does take some time for it to load up for us. That wasn't too bad, right? So here's our instructions up here. Our goal is to use shared structures to show how species are more closely related. This is very similar to our last modeling tool we did, except this one, instead of the environment telling us where things are going to go, we get to choose the new structure, and we get to take our species cards and put them in the correct place. First things first, though, I think we should click the bottom of each of these cards and indicate the organism type first. So let's do that. So hopefully by now we just automatically know that at the top of the tree here, we would have our common ancestor population. We would follow this down and we would see, hey, that would make this a descendant species. Now, this is where things get tricky though. Notice that this comes down and then it branches again. So what would we call this? Well, actually, we would call this a common ancestor population. descendant species of that common ancestor population. Now, what's tricky and unfortunate about this model is if we were talking about species A versus species B, then we would have chosen a descendant species, right? But because our final product is over here, we should say that that's a common ancestor. Okay, so we've got three species, and we on the right here, and we have three boxes. So we need to first choose which structure, which new structure we're gonna have to carry over from species A to species B, and or which new structure, not which one should carry over. So just looking at this card here, it looks like it's going to be a hind leg structure, right? So I'm going to choose a hind leg to make it blue. That will be my indicator. And so we've got no tail, no tail. We're starting to get a hind leg. So we're going to choose this one with no tail. And this one has a hind leg, but notice its front one has gotten a little smaller. So now we're going to do the same thing. So for this new structure, oh, we've got to do the split here. So here's our other one with no tail. We're going to put that one in there. Notice we've got our hind legs as our new structure at this juncture. So that would leave just on this one to go here, and that would mean that it looks like our new tail is the new feature of this critter. So we can see, for whatever reason, the change in the environment that happened here for species B and species D. One of them was advantageous to have a tail, one was advantageous to have hind legs. And then with this split in the environment, we see that one of those environments, it was better to have a smaller front limb, and one of those environments, it was beneficial to have a larger front limb. Go ahead and push this hand in button, and that should take a screenshot automatically for you and dump it out here into Amplify. And you're done with part 3. Let's go ahead and move on to the homework section. So, you have two models here. Now, this is kind of abstract, and this is sort of what we did in the hands-on here. So you're still getting a little piece of it. So we are seeing an evolutionary tree, two of them, and we see shared structures that are being passed down from generation to generation, but one of these is incorrect, and only one of them is correct. So what you need to do is you need to look at these shared structures. So we've got a pentagon, 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 square, 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 with some different appendages here. Here we've got a pentagon and a trapezoid, and we've got a trapezoid here and a trapezoid here with different shapes or appendages there for model 2. For model 1, pentagon, 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 that all checks out. But notice how the square kind of drops off. We've got a square, and then all of a sudden that just adds a triangle, the D species, where the B species drops everything and just starts adding new stuff. So it's losing some of those shared structures. And you might notice that same thing is happening here, where all of a sudden species C lost its trapezoid and decided to gain a square, like up from model A. So looking at these two, which one of these two do you think is correct? Model 1 or model 2? And then I want you to explain your thinking here. All right, friends. The correct answer, we should say which model is correct. It should be 2. Notice how each time this splits at this level up here on this model, we're losing structures and gaining structures kind of randomly, whereas here we're actually seeing those structures that are picked up at this level passed on to this descendant population. So let's go ahead and go to page 2 of your homework, and we're going to be looking at babies, little embryos. So read this article comparing embryos, evidence from common ancestors. Read this article and then answer these two questions down below. Push your hand in button, and you will officially be done with lesson 3. What was it? 3.1. Awesome. Don't forget to like, share, comment, subscribe, and don't forget, be nice.